Alistair Cameron is a leading authority on the origin of the solar system, and for some years he has been exploring this fascinating problem at Harvard University in the USA.
Now, of course, initially, my ideas were very different from what they are now. In fact, I remember I gave a lecture at the Institute for Advanced Study in Princeton on my then views a long time ago. And Robert Oppenheimer, who was then the director, listened to this, and his devastating comment at the end was that that was all very well, but he thought he still preferred the biblical original.
Cameron's present theory is one of a number which have occupied center stage for some time. These are the solar nebula theories, in which the sun, and indeed the whole of the solar system, forms from one and the same fragment of a molecular cloud. Now, in all such theories, one is free to a certain extent to choose the initial conditions of the fragment. And these initial conditions will determine, to a large extent, how the fragment evolves. For example, Cameron chooses the mass of the fragment to be about twice the mass of the sun, about twice the present mass of the solar system. Well, from this initial condition and from others, he shows that at the center of the fragment, there forms a flattened disk of rather denser material. Now, the evolution of this disk can be divided into 3 stages. This is a region within a molecular cloud, a tenuous mixture of gas and dust, from which a fragment separates and begins to condense. Notice that the fragment is rotating. It has angular momentum. Notice also the infall of matter to build up denser material into a region known as the disk or nebula. The build-up of mass of the nebula or disk is known as stage 1 in its evolution. Stage 1 is now complete. Build-up has ceased. Initially, there is little mass in the center, perhaps not quite what you had expected. Dissipation of matter inside the disk gradually begins to build up the mass of the sun. This is the beginning of stage 2. This is a side view of the disk at that stage. You can just see brightness in the center representing the growth of the sun there. But notice how much mass there is in the outer regions as well. And notice how relatively thick the disk is towards its periphery at this time. Up to now, the material within the disk has been very turbulent. This turbulence quietens down and eventually ceases altogether, bringing us to stage 3, a non-turbulent disk. You can see that enough mass has accumulated at the center to form the sun, although there is still a large amount of matter in the outer region of the disk as well. This is the usual Hertzsprung-Russell diagram, with the sun at its present luminosity shown for reference. But when the sun has just finished growing, and regardless of whether it grew in the way Cameron suggests, it is pretty certain that it was a good deal more luminous than it is today, perhaps 20 or 30 times more luminous, placing it here. So what effect does this high luminosity have on the disk? Remember, we're at stage 2. The disk is highly turbulent.
Here we are, with the sun having formed with its present mass, perhaps a little bit more than its present mass, and putting out this very large amount of energy. The dissipation process in the disk depends upon the presence of thermally driven turbulence, that is, thermal convection. If the energy output from the sun is too large, then the top and bottom surfaces of the disk will be greatly heated by that output, and it will no longer be possible for thermal convection to operate in the interior. Therefore, a hot, luminous sun may be able to thermally suppress the turbulence and stop the dissipation of the disk nearby. Now, we must remember that the formation of the sun is not something which occurred in isolation. Rather, we are forming a whole cluster of stars close to the region where the sun is forming. They are all around here, shall we say. These massive stars are likely to put out so much energy in the interior of this collapsed cloud that the outer periphery of the primitive solar nebula is also likely to be heated enough to suppress any thermally driven turbulence within it. So, in this way, we lead gradually into the third stage in the evolution of the solar nebula, in which turbulence is suppressed and in which the mass has perhaps fallen quite low in the region of planet formation, perhaps to about 1% or so of the present mass of the sun. Further out, there may be quite a lot of mass, and we'll come back to what happens to it shortly. But this third stage of thermal stabilization may last for rather a long time.
We must now consider the formation of the planets. This means that we must backtrack in time to stage 1 in the evolution of the disk.
Let us start with the outer planets. And to do that, I want to first tell you about some characteristics of the outer planets that have recently been deduced from the recent spacecraft observations of Jupiter and Saturn, and from the studies of the motions of the satellites of Uranus and Neptune that have taken place. As a result of these studies, we know much more accurately than we did before values for the gravitational moments of these outer major planets, and we therefore have a basis for making models of the interior. The best of those models, the most recent ones, appear to be those of David Stevenson at the California Institute of Technology. What Stevenson has found is that the cores of the major planets all seem to be about 10 Earth masses composed of something much heavier than hydrogen and helium, presumably rock or icy materials. The interesting aspect of that is that if one wished to form those cores by letting rock or icy material come in at the surface and try to penetrate down through the outer mantle of hydrogen and very dense helium, which exists near towards the center of the planets, then the rock and the icy materials would actually dissolve into that hydrogen and helium. It could not get through to form the core. Therefore, we conclude that the cores are in some sense primordial. They must have been formed for the most part before that huge overlying set of mantles of hydrogen and helium were obtained by the planets. Now, in order to do that, we must have first the cores. We must immerse the cores in the gas of the primitive solar nebula. We must let that gas concentrate gravitationally toward the cores and then collapse onto the cores. Can we do that in the outer part of the solar nebula where the major planets are now? There are major difficulties. One of the problems is to form very massive cores out there in a reasonable time. Many people have worked on the theory of planetary accumulation involving the mutual collisions among many, many small solid bodies within the primitive solar nebula. And the conclusion reached by many such studies is that Neptune is in great difficulties. It appears that the time required to form Neptune must be some thousands of millions of years, probably very much longer than the time required to eliminate the remnants of the solar nebula altogether. So how does one get a massive core of something like 10 Earth masses out into the position of Neptune in a reasonable time? Probably only by forming it much closer to the center of the primitive solar nebula. Is there a way to do that? There may very well be. Now, initially, as the disk builds up in mass, there will be a tendency for those regions of it which are a little denser than the average due to statistical fluctuations to become unstable against collapsing on their own right. These instabilities, and we can imagine that there are many of them around here, are likely to form upon collapse what I call a giant gaseous protoplanet. Many more of them than there are planets today. And these giant gaseous protoplanets had their envelopes stripped away by the rising temperature of their surroundings, but probably not before clumps of interstellar grains were able to drift down through the gas, collect at the center, and form cores which may have been perhaps one Earth mass, perhaps less, perhaps several Earth masses. It appears that in stage 2 of the evolution of the nebula, when the surface density of the nebula was large, tidal interactions between the cores of giant gaseous protoplanets and the gas would succeed in transferring angular momentum from the gas to the cores to a great extent, sufficient to move them well out in the primitive solar nebula. And in this way, it may very well be that the cores about which Jupiter, Saturn, Uranus, and Neptune formed were positioned in a suitable place in the outer solar nebula. Then it is possible for the surrounding gas to become concentrated toward them, to collapse onto the cores, and we have the major planets in that way. I want to show you some sections taken through the solar nebula according to some recent calculations of mine, which show really how hot the conditions may have been there. This is a situation that one might expect about halfway through the buildup of the sun. That is to say, at the center of the nebula, at the time this represents a section, we have about a half a solar mass at the center. We have the radial distance in astronomical units along the bottom axis. On the vertical axis, on a different scale, you'll notice, is the height of the nebula in units of a tenth of an astronomical unit. Notice that the nebula is quite thick. For example, at a radial distance of 1 astronomical unit, it's between 0.2 and 0.3 astronomical units high. These lines in the nebula are lines of constant temperature. The temperature is really quite high, going from about 1,000 degrees Kelvin along this line to about 1,800 degrees Kelvin along this line. And now I want to show you where on this diagram solid materials will be condensed and where they would evaporate. What we see here is the lines along which metallic iron will condense. It will be in condensed form everywhere to the right of this curve and above it, and also where a form of magnesium silicate called forsterite will condense. It will be in condensed form everywhere above and to the right of the second line here, and both of these will be evaporated toward the lower left. There are some materials more refractory than iron and forsterite, containing calcium and aluminum and materials of that kind. they will all have evaporated along what is called the evaporation frontier. They're condensed toward the right and above, evaporated down here. So in this diagram, everything essentially has evaporated toward the center and near mid-plane. Of course, if we have any planetary bodies, they're at mid-plane or close to it. What counts is where these various evaporation lines cross mid-plane. Now let us consider where an object having the same specific angular momentum as Mercury would be in this diagram. Remember, we have only half a solar mass at the center of the disk. Therefore, Mercury would be twice as far away as it normally is. It would be out here close to 0.8 astronomical units. But it is inside the evaporation front already by the time the Sun has grown to half its present mass. By the time the Sun has grown to a full solar mass, the condition is even worse. Mercury would have spiraled inwards, conserving angular momentum, to close to 0.4 astronomical units. This region will be even hotter than shown. In other words, Mercury is in a region where silicates, iron, calcium and aluminum oxides, everything wishes to evaporate. Under these circumstances, it is very hard to see how Mercury could be formed by bringing small bodies together at this distance. There appears to be only one way in which one can do it, and that is to make use of the cores of giant gaseous protoplanets which were formed in the inner solar system way back before there was any significant amount of mass in the Sun, when there was only a little bit of mass in the primitive solar nebula, and when the giant gaseous protoplanets condensed, then had their envelopes thermally evaporated away, and when the cores of condensed materials were left behind. Mercury is a very anomalous planet in that the ratio of iron to silicates is much higher than normal. If we ask what would we need to do to Mercury to make it have the same iron to silicate ratio as in the Sun, let us say, we would need to make it about twice as massive as it is now, adding a great deal of silicates to it, presumably in the form of an outer mantle. Mercury, being formed as a core of a giant gaseous protoplanet, in such a position as this, is therefore likely to have the outer silicates vaporized, leaving behind a silicate-poor planet of much reduced mass, which Mercury appears to be today. And if Mercury is formed in this way as a remnant of a core of a giant gaseous protoplanet, then probably the other terrestrial planets as well, Venus, Earth, Mars, are formed by a similar process.
The inner planets have thus acquired their bulk compositions. But Venus, the Earth, and Mars also bear traces of volatiles, which make up interesting things like oceans, atmospheres, and so on. As yet in Cameron's theory, they bear no such volatiles. Now, how does he get around that difficulty?
Let us progress forward in time to the third stage in the evolution of the primitive solar nebula, the thermally stabilized stage in which turbulence has died away. Turbulence mixes up the gas and any small particles within it throughout the full height of the primitive solar nebula. That turbulence, once it disappears, allows the solid particles within it to gradually precipitate out, to fall through the gas toward mid-plane, where they can form a thin layer of condensed materials. Once at mid-plane, this material becomes unstable against gravitationally collecting together to form bodies of asteroidal size, that is to say, a few kilometers in radius. And these bodies, being formed cold, have lots of the more volatile elements within them. The inner planets collect their share of these asteroidal-sized bodies gravitationally, and thereby are able to obtain the more volatile elements.
Such asteroidal bodies would have formed throughout the solar nebula, and we see some survivors today between Mars and Jupiter. Now, those that formed beyond Neptune would have been icy, and Cameron proposes that these are the comets. Indeed, it is widely believed that out there is a vast cloud of comets, the Oort cloud. But today they lie at about 50,000 astronomical units, whereas in Cameron's theory, they initially lie at only a few hundred astronomical units. How can they be made to move further out? At this stage, there are several tenths of a solar mass of material beyond Uranus and Neptune. Consider a comet in orbit outside of this material. Suppose that by some means, to be considered shortly, the material is removed in a time comparable to or less than the comet's orbital period. Then the orbit would change into a much elongated ellipse. It might even escape the solar system altogether. For this to work, the material must go in a few thousand years.
But how would we remove this mass in such a short time? Probably not due to anything that the sun does. Probably only by having some of the neighboring stars, which are forming at the same time as the sun, become very hot, very luminous, and heat this outer material to a high enough temperature so that it can thermally evaporate from the solar system quite quickly. If that is what has happened, then the comets formed at 1 or 2 or 300 astronomical units may have their orbits elongated out into the region of the Oort cloud, whereby passing stars can circularize those orbits and scramble the orbital elements quite efficiently in the 4,500 million year history of the solar system. We started with forming the sun. We wound up considering the formation of the comets, a major, often overlooked element of the solar system. The theories put together to try to understand that have in fact changed a great deal in the course of the last year. I would not be at all surprised if they did not change again a great deal in the course of the next year. But the process of trying to understand this is most exciting, and the whole subject of understanding the origin of the solar system is becoming one that can increasingly be described as a scientific process.
Cameron describes his present views as a medley of theories rather than as a single theory. But the important question is he right?
The confirmation of a medley of theories, such as I have described, is not something which is easily done, because you may confirm or deny any one component of that medley of theories, causing it to be replaced by some other component of the theory. And in fact, that really is what happens as one gets observational evidence that bears on some part of the theory, or a computational result which also bears on the theory. One's ideas change. Hopefully the changes result in improvements, but anyway, for good or for bad, it is described as scientific progress.